welcome to another module in this massive open online course on estimation for wireless communication systems. So, in the previous module we have looked at sequential estimation, that is how to keep continuously updating the estimate based on the received observations, that is sequentially updating the estimate and also the variance of the estimate, all right. So, today let us look at an example to understand this paradigm better. So, what we want to look at today is an example for sequential we want to look at an example for sequential estimation, all right. So, let us start by considering the same paradigm that we are considering before, that is wireless channel estimation. Let us start by considering n is equal to 3 samples. Remember, sequential estimation involves computing an initial estimate at n and then later updating it to the estimate at time instant n plus 1 once the n plus 1th observation is derived or once the n plus 1th observation is made. So, we will consider the same example that we have seen previously for wireless channel estimation, except now we will estimate the wireless channel sequentially. So, previously we considered an example with n equal to 4 symbols. Now, what we are going to do? We are going to modify the same example to basically start with n equal to 3 symbols, that is the transmitted n equal to 3 pilot symbols, received n equal to 3 pilot observations, compute the estimate at n equal to 3, all right, and then consider the arrival of the n plus 1th observation at n equal, that is n plus 1 equal to 4, and then demonstrate how the update or how the estimate h hat n plus 1, that is h hat 4 is computed as an update of h hat 3, the estimate at time n is equal to 3. Okay. So, let us consider the 3 pilot symbols, consider the 3 pilot symbols. Or rather consider the n equal to 3 pilot symbols. The n equal to 3 pilot symbols, let us say they are given as similar to what we had considered before, that is x 1 equals 1 plus j, x 2 equals 1 minus j, and x 3 equals 2 minus j. Now, one important observation that you can make here is that we are considering complex pilot symbols. However, in the framework for sequential estimation, we considered only real symbols and real parameters. Okay. So, what we are going to do now is during this example, I am going to illustrate how to extend the framework of sequential estimation to a complex parameter, and that is going to be fairly simple. All right. So, just to bring to your notice, we are considering complex symbols. So, the framework of sequential estimation. So, we will see how to extend, we will see later how to extend to complex symbols. Okay. So, therefore, our vector, pilot vector x bar, remember x bar, what is this x bar? This is the pilot vector, and this is given as x 1, x 2, x 3, that is basically 1 plus j, 1 minus j, 2 minus j. This is your pilot vector, which is basically n cross 1 or basically 3 cross 1. And similarly, let the received symbols be let the received output symbols be y 1 equals, well, y 1 equals 3 plus 5 j, y 2 equals minus 5 minus 3 j and y 3 equals 2 plus 3 j. All right. So, we have corresponding to the three transmitted pilot symbols x 1, x 2, x 3, we have the 3 received pilot symbols y 1, y 2, y 3, and therefore, we have the received vector y bar, which is formed from y 1, y 2, y 3, and that is given as y bar equals 3 plus 5 j minus 5 minus 3 j 2 plus 3 j. Therefore, the estimate h hat, we already know how to compute this. Therefore, the estimate h hat is given as, we have h hat of 3 is x bar Hermitian y bar divided by x bar Hermitian x bar, that is basically again you can write this as x bar Hermitian y bar divided by x bar. Hermitian x bar is basically your norm of x bar square. Okay. And therefore, now you can see norm of x bar square is simply the sum squared of the sum magnitude squares of each of the components, 1 plus magnitude 1 plus j square plus magnitude 1 minus j square plus magnitude 2 minus j square, that is well 2 plus 2 plus 5, which is equal to 9. Okay. So, norm x square equals 9, and x bar Hermitian y bar, again Hermitian is nothing but the transpose and conjugate of each element, that is 1 minus j, 1 plus j, 2 plus j times your vector y bar, that is the same as before, that is the column vector y bar. So, what is this? This is your x bar Hermitian times y bar is basically 3 plus 5 j minus 5 minus 3 j and 2 plus 3 j, this is your vector y bar, and therefore, this can be simplified as this is equal to, well, that is your 1 minus j times 3 plus 5 j plus 1 plus j times minus 5 minus 3 j plus 2 plus j into 2 plus 3 j equals 7 plus 2 j. Therefore, we have evaluated x bar Hermitian y bar as 7 plus 2 j, and we have also evaluated norm x bar square or x bar Hermitian x bar, which is 9, and therefore, the ML estimate at time instant 3, that is h hat 3, is given as x bar Hermitian y bar divided by norm x bar square, which is equal to. So, we have h hat of 3, which is basically your ML estimate at time instant 3, that is basically 7 plus 2 j divided by 9, which is nothing but 7 divided by 9 plus 2 divided by 9 j. So, what is this? This is your ML estimate at time instant 3. ML estimate at time instant 3, ML estimate of the channel coefficient of course. Yeah. Now, the other thing, remember the other thing that we have to compute in the sequential process, the sequential estimation process is basically the variance at time instant 3. The variance Pn at time instant 3 is sigma square divided by norm x bar square, alright, we know that also. So, the variance Pn at time 3, that is P of 3, variance of the estimate at n equal to 3, that is basically P of 3 equals sigma square divided by norm x bar square. Let us consider similar to the previous example in the wireless channel estimation, let sigma square, let the dB variance let the dB noise variance be 3 dB, which implies 10 log 10 sigma square equals 3, which basically implies your sigma square equals 10 power 0.3, this is approximately 2. Okay. So, 3 dB noise variance, right, 3 dB noise variance basically corresponds to a sigma square value of 2. Okay. So, now the noise variance P 3 at time n equal to 3 is sigma square divided by norm x bar square. So, this P 3 equals sigma square divided by norm x bar square, which is sigma square is 2 divided by norm x bar square is 9. So, this is basically your value of P 3. So, we have calculated h hat of 3, which is the estimate at time instant n equal to 3, and P 3, which is the variance at time n equal to 3. Now, let us assume that now consider the received transmitted pilot symbol x n plus 1 at time instant n plus 1, that is n equals 3, therefore, n plus 1 is 4. That is consider the transmission of x 4 and the reception of the pilot's output pilot symbol y 4, that is y n plus 1, and now basically using h hat of 3, we would like to estimate it to h hat of 4, okay, at time instant n plus 1. So, consider now the transmission of pilot symbol x n plus 1, that is x of 4. Remember n equal to 3. So, we are considering the transmission of x of 4. Corresponding received symbol is y n plus 1, that is y of 4. Okay. So, let x n plus 1 equals, remember let x n plus 1 equals x of 4, let this be equal to 1 plus 2j, and let the corresponding output symbol y n plus 1 equals y of 4, and let this be equal to minus 3 minus 2j, and therefore, the prediction error E n plus 1 equals E 4 equals y n plus 1 minus, remember we said h hat n times x n plus 1. Remember, for the sequential estimation process, we have to compute the prediction error E n plus 1 at time instant n plus 1, that is E4, which is basically that tells us how accurate is the estimate h hat n computed at time instant n, and it is defined as y n plus 1 minus h hat n times x n plus 1. Okay. And therefore, now I am going to substitute y n plus 1, y n plus 1 we know y n plus 1 is given as, well, that is already given, that is minus 3 minus 2j minus h hat of n, h hat of n is 7 plus 2j divided by 9, that is what we already computed. Remember, this is h hat of 3. Just to write it a little bit more explicitly, this is basically your y 4 minus h hat of 3 times x 4. So, 7 plus 2j over 9 times 1 plus 2j, and this is equal to, well, I can simplify this, this is minus 3 minus 7 by 9 plus 4 by 9 minus j times 2 plus 2 by 9 plus 14 by 9, which is equal to minus 30 by 9 minus 34 by 9 times j, and what is this? This is your prediction error E hat n plus 1, that is E hat of 4. This is your prediction error at time n equal to 4. Prediction error at time, this is your prediction error at time n equal to 4. So, for the complex quantities, now we have to come up with the update equation. Remember the update equation which we said previously, let me first write the update equation for the real symbols, right. The update equation this is the update equation for h hat n plus 1, which is the estimate at time n plus 1. Which is the estimate at time n plus 1, and the update equation, remember, is given as h hat n plus 1 equals h hat n plus k n plus 1, where k is the gain, times E n plus 1, where E n plus 1, this is the prediction error. So, k n plus 1, remember k n plus 1 is the gain at time So, naturally for complex symbols, what I am going to do is I am going to do a simple modification. I am going to simply replace this k n plus 1 by k conjugate for complex symbols, where the conjugate that is it, that is the simple modification that we have to do, that is replace the gain k n plus 1 by k n plus 1 conjugate, because we are considering complex symbols x n and complex received output symbol y n, and similarly complex symbols x n plus 1 and received output symbols y n plus 1. So, I am replacing the gain k n plus 1 by the complex conjugate. Okay. And one more small modification, if you look at the expression for k n plus 1, we have k n plus 1 equals, remember we had defined k n plus 1 as P n, the variance at time instant n, divided by x n plus 1 divided by sigma square, the noise variance, plus P n times x square n plus 1. Now, I am going to replace this by the magnitude square. All I am going to do is I am going to replace by the magnitude square, that is magnitude square, replace this by the replace this by the magnitude square for your complex symbol x n plus 1. All right. So, there are two changes basically, one is k n plus 1 is replaced by the complex conjugate, all right, that is k n plus 1 conjugate in the update equation, and in the expression for k n plus 1 instead of x square n plus 1 I have magnitude x n plus 1 whole square. Okay. So, now using this let us compute k n plus 1, the gain at time 4 set at that is n equal to 3. So, k n plus 1 equals k 4. So, k 4 equals basically P 3 times x 4 divided by sigma square plus P 3 times magnitude x 4 square. Okay. We have computed P 3 before. P 3 is the variance at time 3, that is 2 over 9 times x 4, that is 1 plus 2 j divided by sigma square, which is 2 plus P 3, which is 2 over 9 times magnitude 1 plus 2 j whole square, which is equal to 2 over 9 times 1 plus 2 j over 2 plus 2 over 9 times magnitude 1 plus 2 j square is 5. This is basically 1 plus 2 j divided by 14. Okay. And what is this? This is your k 4, that is gain, complex gain at time n equal to 4, n plus 1 equal to 4. Okay. Complex gain at time n plus 1 equal to 4. And now the update equation therefore is h hat, therefore the update is h hat 4 equals h hat 3 plus k conjugate 4 into E 4. We know h hat 3 is 7 plus 2 j divided by 9 plus k 4, we have already calculated that here. So, I have to take k conjugate 4, that is 1 minus 2 j divided by 14 times E 4, which is basically the prediction error, minus 30 by 9 minus 34 j divided by 9, and this is basically equal to, now I am going to simplify this, 7 by 9 minus 30 divided by 9 into 14, you can check the calculation, minus 68 divided by 9 into 14 plus j times 2 by 9 plus 60 divided by 9 into 14 minus 34 divided by 9 into 14. This can be simplified as this is equal to, well, this is 98 minus 30 minus 68 divided by 9 into 14 plus j times 28 plus 60 minus 34 divided by 9 into 14. This you can see this quantity is 0. So, this is basically, and this reduces to 54 times j divided by 9 into 14, which is basically 6 j divided by 14. And what is this? This is the estimate at time instant 4. and this is similar, and what you observe interestingly is exactly identical to the maximum likelihood estimate we calculated in the previous example. In the previous example for wireless fading channel estimation, considering 4 transmitted pilot symbols, that is n equal to 4 transmitted pilot symbols and n equal to 4 received outward pilot symbols. And what we observe is that using this sequential estimation procedure, we basically get back the same estimate h hat 4. All right. So, let me just highlight that h hat 4 equals, what is that, 6 j or 6 divided by 14 times j, which is basically ML estimate, identical to ML estimate for n equal to 4. This is identical to the ML estimate for n equal to 4 pilots computed previously. In previous example. By previous example, I mean the previous example for maximum likelihood estimation of the wireless fading channel coefficient. Okay. All right. So, now we have to compute the variance. Remember, we have to compute the variance. At every step, we have to compute both the estimate and the variance in the sequential estimation procedure. Okay. And the variance update, you remember variance update for the real case is given as P n plus 1 equals P n into 1 minus K n plus 1 into E n plus 1, K n plus 1 is the gain, E n plus 1 is the prediction error. Now, for the complex scenario, naturally all I have to do is replace this gain by the conjugate for your complex symbols. For complex symbols, K n plus 1 is replaced by K n plus 1 conjugate, and that is the only change, and therefore, P of 4 equals P of 3 1 minus K conjugate 4 into prediction error E 4, which is P of 3, we know this is 2 over 9 times 1 minus K conjugate 4, which is 1 minus 2 j divided by 14 times 1 plus 2 j, which is equal to, well, 2 over 9 into 1 minus 2 j into 1 plus 2 j is magnitude 1 plus 2 j square, which is 5 divided by 14 equals 2 over 9 times, well, 14 minus 5, that is 9 divided by 14 equals 2 over 14 equals 1 by 7, and what is this? This is P 4, prediction error at time n equal to 4, and this is basically the prediction, I am sorry, this is the variance at time n is equal to 4, that is basically the variance in the estimate h hat of 4, that is this quantity is basically nothing but, you all know, this is the variance in the estimate, that is expected value of h hat 4 minus h square, that is variance in estimate computed at time n equal to 4 or n plus 1 equal to 4, basically n plus 1 is the next time instant, correct. So, what we have calculated, what we have shown in this example is basically we have calculated the estimate h hat 4, which is 6 j by 14, which is identical to the previous ML estimate, and in fact, you can also check the variance P of 4 equals 1 by 7 is also identical to the variance computed for the previous maximum likelihood estimate. And in fact, we had proceeded further to derive that the variance of the errors of the real and imaginary parts are uncorrelated, and the variance of the real and imaginary parts of the estimates estimate is basically half of the total variance, that is the variance of the real part of the estimate is 1 over 14 and variance of the imaginary part is also 1 over 14, and that also holds again, it is natural that that also holds basically in this sequential estimation procedure. Alright. So, what we have described here, what we have shown in this module is a detailed example of basically the paradigm of sequential estimation illustrated in the context of estimation of a wireless fading channel coefficient. Naturally, this can be extended to other scenarios also, for instance the wireless sensor network very easily. It can also be extended to the vector estimation scenario, that is the downlink multiple antenna channel estimation OFDM and other scenarios, although extension to the vector case is not very straightforward, but it has a similar structure which we will defer to a slightly later course probably, because it is slightly more complicated than this. But basically what we have shown is, we have shown described this paradigm of sequential estimation, which is very interesting because we do not need to recompute the estimate at every time instant, rather simply update the latest or the previous estimate. All right. So, we have shown how to compute, update the estimate, the update equation in terms of the gain and the prediction error, how to compute the updated estimate, and also how to update the variance at every time instant. So, this, and basically we have also shown that this yields exactly identical results as that of the ML estimate, which is basically the one shot estimate computed at every time instant, and naturally because the sequential estimation procedure itself was derived from the ML estimate. All right. So, we will stop this module